The red light is now on. Hey guys, what's going on? Memes here. I'm joined by physicist Jonathan Gorard. Say hi to the folks, Jonathan.
Hi, everyone. Good to be here.
All right. And this is actually a treat for me. Well, the reason why I say this is because over the past year, as we were just talking a little bit, Jonathan, I happened to come across your work whilst working on the Wolfram physics project, and I got a chance to read one of your papers the other day. And I'm going through it, and I'm like, this is fascinating. I've heard many of these words before. I don't always know what they mean. And then, in order to not take the entire night and reading through your paper, because every time I'm like, okay, let's look at Wikipedia. Let's look what this is. Okay, oh, there's a transformation of the Boltzmann constant. That's very important here. And I keep going on and on. I'm like, I'm seeing more triangles. That's a tetrahedron. Oh, that seems to be in 4 dimensions there. That's very fascinating. So, in the way of the great maker J. Michael Straczynski, the creator of the hit sci-fi series Babylon 5, Jonathan, who are you?
Who am I? That's a deep question. I'm not entirely sure I know the answer to that. I can describe. There's a tendency in maths to talk about an object in terms of what it does, in terms of what its actions are. So maybe I should do that about myself rather than.
Sure.
It's like you describe a group in terms of its action rather than in terms of its internal properties. So. Yeah. Okay. So hi. I'm Jonathan. As Memes mentioned, I used to work on this thing, and still to an extent do work on this thing called the Wolfram Physics Project, which I co-founded and was associate director of research for. And so my day job is I'm an academic mathematician. I work at the University of Cambridge, and I'm kind of interested, broadly speaking, in the interface between pure mathematics, theoretical physics, and theoretical computer science. So I'm interested in how the foundations of math, the foundations of physics, and the foundations of computation are essentially related to one another. How effectively, really, math lies at the basis of physics, and computation lies at the basis of math, and somehow also physics lies at the basis of computation. And a lot of my kind of academic research involves trying to understand that slightly kind of weird, ouroboros phenomenon. So a lot of my research is focused on sort of quantum gravity, particularly discrete models for quantum gravity. So trying to describe sort of the fundamental structure of space-time in terms of as a discrete mathematical model. And a lot of my more recent research has been trying to apply some methods that come from fairly abstract parts of mathematics, particularly higher category theory and higher topos theory, that kind of are conventionally viewed as being part of logic or topology, and trying to apply those to better understand the foundations of physics, particularly the foundations of both quantum mechanics and quantum gravity. I work on some other things as well, but that's probably that's a reasonable summary of the headlines.
You are also a player of the Call of Cthulhu, I hear, and we can see.
I have just very recently started a new Call of Cthulhu campaign. This is true, yeah. And this explains the slightly strange conspiracy theory-esque background.
Well, I mean, it's all connected there, and it's very interesting because every once in a while I end up getting back to the model. I'm like, so what if life was like Dungeons and Dragons? Or some form of a game and stuff. And like, all right, you're going to give it these parameters. I sit back, I'm like, no, that can't be. And I sit back and I actually think about it. I'm like, one could actually probably build a decent model of it. And that's kind of like one of the reasons why I wanted to have you on, because of a lot of your modeling that you've used. And just the sheer fact, it's like, all right, you start a model in less than a year. It's like, yeah, we got special relativity and we're working on, oh, okay, we got GR. And I'm like, that's very fascinating. Could you just kind of go over some of the tools that you use, like whether it's the hypergraphs, and I know there's kind of several different forms of those, kind of give the folks a little bit of a generalized overview?
Yeah, okay. So the basic idea is, we traditionally think of physics in terms of like continuous mathematical structures. So we think of like space and space-time as being these kind of smooth spaces where you can define continuous functions and things like that. And also in more abstract contexts, when you deal with, say, quantum mechanics, even there we think of the space of quantum states as being a Hilbert space, some kind of smooth continuous space. The question is sort of what if that's not really kind of what's going on at the foundation of things, right? What if the fundamental ontology of reality is more like a discrete mathematical structure, which just resembles a kind of continuous space on a sufficiently large scale. And there's kind of already good reason to believe that something like that might be true, just based on the little that we already know about quantum gravity. So, for instance, one of the reasons why quantum gravity is difficult is because gravitation has this effect called an ultraviolet divergence, which essentially means that if you try to write gravitation down as a quantum field theory, you can do it. You can write down sort of an action integral that defines the gravitational action in the framework of something like a Yang-Mills theory or some other form of quantum field theory. But the problem that you encounter is that unlike other quantum field theories that you might write down, when you try to actually compute quantities with it, if you try to compute scattering amplitudes or something, you get this rather unwelcome effect, which is that the contributions to your action integral get larger and larger as you go to higher and higher energy scales or smaller and smaller length scales. And so you get what's called an ultraviolet divergence, that your action integral kind of diverges off to infinity and you don't get sensible answers for your scattering amplitudes. And with some other quantum field theories, there are procedures by which you can renormalize this and get some finite answer by a process called regularization, which effectively lets you absorb the infinities into these physically relevant quantities. But for the case of gravity, you can't do that. You get an unrenormalizable infinity. So one of the ways that you can get around that people have investigated now for the best part of 50 years, is that you can say maybe space-time is fundamentally discrete. Maybe there's like a minimum length scale below which the structure of space-time is no longer well defined. And if you do that, that immediately imposes a cutoff, an ultraviolet cutoff, which means that you're now limited in how large the energy scales can get, and therefore how large the contributions to your action integral can get. And you get this thing called lattice regularization, which lets you write down a sort of asymptotically safe gravitational sort of quantum gravity model that's free of ultraviolet divergences. So and all you need to do is postulate that space-time is discrete. So there are already good reasons to think that the structure of space-time might not be continuous all the way down. So the question is then, what would it look like if you didn't, we have whatever 350 years or something of experience of building physics models based on continuous mathematics since the time of Newton. What would it look like if we built physics not based on continuous mathematics? If we built, if we built structures based on discrete mathematical formalisms? So the approach that we adopted in the Wolfram Physics project, and the approach that I'm kind of trying to continue in a lot of my more recent work, involves modeling space as just physical space as a graph, as just a network. So you treat space not as a smooth structure, but just as a large collection of discrete points with kind of edges defined between them by the sort of by the lines that in some network, or the lines in some graph. And so those edges define which points of space are sort of adjacent to which other points. And that gives you a kind of minimal model for space. And then what you could do is you can try and write down laws of physics, right? You can try and define a dynamics on that space. So in ordinary physics, you might define laws of physics in terms of, partial differential equations or something. You can't do that with discrete mathematical structures. You have to do something a bit more subtle. So one of the minimal models for dynamics you could write down is just a rule that says, if you've got a piece of the network that looks like this, if you've got a piece of space that looks like this, then replace it with a piece of network that looks like that. And so that gives you what we might call a graph substitution rule, or a hypergraph substitution rule. And then you can just apply that rule, wherever it fits, and you can evolve one of these networks through time. And that gives you a sort of a minimal dynamics for this very simplified kind of model of the universe. And then you can start to do kind of more sophisticated things to sort of analyze the behavior of these kinds of systems. So you could start to ask, what's the causal structure of this rewriting system? So sometimes when you apply a rule, you can have the phenomenon where that rule couldn't have been applied unless a different rule had previously been applied. So there's some kind of causal relationship between the two rule applications. And so you can actually draw a different network, what we call a causal network or a causal graph, some directed graph that shows essentially the map of all causal relations between the updating events. And if the hypergraph gives you a minimal model for space, the causal graph gives you a minimal model for space-time. And one of the things that memes you were referring to earlier is the fact that we know that in a certain class of cases, for a certain class of these network rewriting rules, the causal graph that you get out satisfies both special relativity and general relativity in some appropriate limit. You have to make some assumptions. You have to assume, for instance, that the that the structure of the network is invariant to the order in which the rules are applied, what's called causal invariance. You have to assume that the causal graph has a limiting finite number of dimensions, what we call asymptotic dimensionality preservation. And you have to assume a slightly more complicated technical condition to do with kind of microscopic randomness called weak ergodicity that essentially says that there's no kind of net bias in how frequently rules are being applied in different regions of the network. So you have some roughly homogeneous distribution of rewrites. And as long as those conditions are satisfied, the resulting causal graph obeys special relativity, and what is more exciting, converges to a continuous spatial structure that satisfies the Einstein equations of general relativity. And okay, you've brought up, okay, you have a picture there of this is a slightly more abstract sort of mathematical model. This is, so what I've just been talking about previously is kind of a minimal model for kind of classical physics.
Should I scroll up or scroll down?
Okay, well, let's see. What have you got here? Okay, so that's that there is a multi-way evolution graph. So what I've just described kind of gives you a way to derive the structure of space, what in mathematics we would call a Riemannian manifold, and the structure of space-time, what in mathematics we would call a Lorentzian manifold. This picture here shows a multi-way evolution graph. This is a procedure by which we can obtain yet another kind of mathematical structure, namely what's called a projective Hilbert space, which is kind of in standard mathematical physics is the setting for quantum mechanics. It gives you the abstract space of quantum states of some quantum mechanical system. And so the meaning of this graph is a little bit different from what I've just been describing. What it says is effectively, when you apply rewrites to one of these hypergraphs or one of these networks, there's no canonical order in which the rewrites get applied. They can be applied in all different orders, and you can get many different sort of sequences of hypergraphs that are not necessarily equivalent, not necessarily isomorphic. So the multi-way evolution graph parameterizes all of these possible evolution histories. And one of the remarkable things that, in fact, was not proved in this paper, but was proved in some earlier work that I did in 2020 and some subsequent work done in collaboration with Monogny and Amaduri and Xerxes Asawala in late 2020 and early 2021, was we were able to show that, in fact, these just as hypergraphs, there's a limit in which hypergraphs give you Riemannian manifolds and a limit in which causal graphs give you Lorentzian manifolds. There's also a limit in which multi-way evolution graphs give you effectively projective Hilbert spaces. But it's a slightly more complicated argument that involves a bit of category theory that effectively says that the algebraic structure of these multi-way systems is the same as the algebraic structure of what's called a compact closed dagger symmetric monoidal category, which happens to be the same algebraic structure as a projective Hilbert space. Anyway, so the big picture point.
I would figure quantum mechanics would probably be a little bit more complicated in that to prove in derivation, but continue, sir. Sorry.
Right. No. I'm basically, all I was going to do was just summarize by saying that so essentially the big picture point I'm trying to make is that starting with these very simple discrete mathematical structures and these very simple rules, we've been able to find kind of appropriate conditions under which we're still able to generate objects that have the same kinds of properties as the continuous mathematical structures that we conventionally think of using in mathematical physics, like space-time, like spaces of quantum states. And we're beginning even now we now have we're starting to get a pretty good picture of how things like SR and GR and also how kind of finite dimensional QM emerge in this kind of picture. And we're just starting right now to chip away at the problem of how we get kind of full infinite dimensional quantum mechanics and also sort of standard quantum field theory, although that's necessarily a much more complicated story.
All I know is you also have a fan in the chat, Jonathan. But
I was trying to pretend I hadn't seen that message.
Yeah, no. Well, I ruin everything. So, but all I'm saying is, and the funny thing is, and again, I kind of apologize for maybe you into a bit of a Harry Potter, but as we were discussing a little bit before the show, I just remember that at one point it's like, okay, so basically I kind of mapped utilizing these tools, these hypergraphs, and I'm looking at a visualization of like two black holes combining, and I'm like, that looks very much similar to what I've seen all these on the fanciest of the science shows and everything. I'm like, except he has measurements and stuff like this. He actually has the numbers that correspond with that. I'm like, he's a wizard. And what I kind of view this as through, at least for just kind of like more of like a sciencey enthusiast noob like myself, is, again, I'm going to bring it back to the games a little bit there. At one point, one of my dungeon masters, he was playing his high-level NPC wizard, and all of a sudden, he'd be like, all right, flesh to stone. It's like rock to mud. And he would just kind of like move this person about and basically just did this huge amount of transformation. And he's like, hold on, wait. And he had to just think in his head. He's like, okay, back to form earth. Yeah, okay, mud to rock to flesh. And it's just going through all these different transformations here. And that's what I'm kind of getting the vibe of with this system. Because as long as there's at least 3 different versions of them, there seems to be some form of a triangulation of like to figure out what's going on.
Yeah, absolutely. So the point you make is really a very good one, right? We've got sort of one underlying system here. We've just got networks with rewrites being applied to them. And yet somehow there are all these different perspectives by which you can look at the results of what happens, right? You can look at it just from the hypergraph evolution. You can look at it from the multi-way system perspective that gives you quantum mechanics. You can look at it from the causal graph perspective that gives you something more relativistic. You can look at it from the branchial graph perspective that gives you something that's more akin to quantum field theory, to quantum information theory in the finite dimensional case and to quantum field theory in the infinite dimensional case. And so these are all sort of slightly different perspectives, but they're perspectives on the same fundamental phenomenon. And we see the same thing in physics. And so this is, I'm going to, I don't want to turn this into like a sort of an advertising campaign for category theory. But, one of the great features of category theory as a mathematical formalism is that it lets you encapsulate a lot of these kind of abstract connections between disparate areas. And so, and there's a particular concept, which is functoriality, that's all about how do you map between kind of one perspective on a structure and a different perspective on that structure that looks radically distinct, but actually preserves enough of the structure that the map has this functoriality property.
Is that like the topos? Is that where that kind of comes in?
Yeah. So a topos is a very specific kind of category that sort of behaves well enough that you can use it as a foundation for a whole bunch of other things.
It's a looser one, I believe.
Well, no. So a category is the sort of most general possible definition. A topos is a very specific kind of category where limits exist for all finite indexes, and which possesses a sub-object classifier or a power set object for every object. And all of that means is that a topos is a category that behaves enough like the category of sets that you can kind of do standard mathematics in that context. And one of the nice features of it is that it's a sort of setting for doing mathematics where spatial structure is sort of fundamental. So in the standard foundations of math, where you just start from discrete sets, or you start from algebraic structure, it's always kind of a mystery where spatial structure emerges from. But when one starts from a topos, particularly what's called a Grothendieck topos, then it kind of already comes equipped with an a priori notion of space, something that's kind of a proto-geometry or a proto-topology from which everything else kind of inherits that spatial structure as you kind of project downwards. So the kinds of functoriality properties I'm discussing I'm referring to in physics, where you can look at a problem from a kind of quantum mechanical picture, and then you can apply a functorial transformation that lets you look at it from a relativistic point of view. Those kinds of functorial transformations do, as you say, tend to be transformations between toposes rather than just between kind of bare bones categories.
Could you give a real quick overview of kind of like, and again, I'm not an overly mathematically inclined. I stopped understanding math halfway through the 6th grade when our teacher's like, you don't need to know this today, but it'll be useful later. So I was doodling in my notebook, and she taught us how to cross multiply fractions. And then I got to the 7th grade and like, so now that you know how to cross multiply fractions, here are some letters. I swear the system just moved me on. The only 2 instances where I really started to understand math were once I got to an upper level finance course in college, and it's like, here's a dollar sign. What project should we invest into? All of a sudden, it's like, I know calculus. That and like nuclear physics and stuff. I needed to have an interest to actually like focus on what was actually going on. Other than that, I was lost. I didn't. All due respect to Adam and Sally, I don't care how many apples they have. Just me. But aside from what is the difference between like a set, a category, and just kind of some like these more basic mathematical concepts?
Yeah. Okay. Well, I mean, maybe it's easiest given the context of this conversation. Maybe I can. I mean, there's an abstract answer to that question, but maybe it's easiest if I kind of describe it in terms of relevance to physics. So, I mean, a set is just, I mean, there's a formal definition that's used in the foundations of mathematics called the Zamiello-Franco axioms, but really you can just think of a set as being a sort of collection of objects. So, in the standard way people like to think about the foundations of mathematics, everything is a set, right? So every integer for, every positive integer is just a set of smaller sets where the positive integer corresponds to the size of that set, or what's called the cardinality of the set. And kind of modern set theoretic or not particularly modern actually, now nearly 100 years old, but kind of proto-modern set theoretic foundations for pure mathematics work by treating everything as being a set underneath. And so if you happened in your sort of high school education or whatever to encounter things like Venn diagrams, those are kind of ways of illustrating basic set theoretic concepts, right? The notions of such and such an object is an element of a set, or one set is kind of the intersection of two other sets, or another set is the union of two other sets, etc., or one set is the complement of some other set, etc. And because set theory has been kind of the standard foundation for mathematics for at least 100 years or so, it's also been the kind of standard foundation for a lot of mathematical physics. And so in particular, the sort of standard way that one formalizes quantum mechanics has tended to be set theoretic. So when you think about a quantum system, you describe its set of, or its space of quantum states, where that space is just a set equipped with some additional structure. So it's what's called a Hilbert space, which then essentially just means it's a set that lets you do things like take projections and measure distances and things like that, but between elements. Whereas,
I'll go on.
Right, please go on.
No, wait. Just by the diagram here, as you were saying, the Venn diagrams, I just went over to our old friend Wikipedia here, and basically it seems like you got two different things, and they have some commonality.
Right, exactly. So you could have, you could have a set of animals, and you could have a set of things that are black, and then you could take an intersection between those things, and that would give you the set of animals that are also black. And so category theory, on the other hand, is a slightly different way of kind of formalizing the foundations of mathematics, which is where you think of, instead of just having sort of collections of objects, you have collections of objects, and you also have kind of methods of transforming between them, which are called arrows or morphisms. So you can represent a category. If you think of a set as just being a sort of bag of stuff, you can think of a category as being just a collection of arrows that map between different structures. And so set theory is a kind of subset of, or is a sub-discipline of category theory in some sense, right? Because you can have the category of sets where every object is a set and every arrow is a set valued function. And sort of there are various nice things about category theory. As I say, one of them is that it lets you kind of visualize the differences or the commonalities between different fields of mathematics or different fields of physics in a very natural way, using properties like functoriality, which is essentially the statement that you can transform one category into another in a way that sort of preserves the structure of the morphisms or the arrows. But to put the more physics-oriented perspective on it, the way I like to think about it is that sort of set theory, if one thinks about the foundations of quantum mechanics, set theory kind of treats the notion of a state as being fundamental, whereas category theory treats the notion of a process as being fundamental. So when we think about a quantum system, you've got, to take the simplest quantum system that one studies in quantum information theory, take something like a qubit, just a system that has two possible states, like a spin up or a spin down. Then what you can do is you can say, so at every point that particle, that system is in some state, and we can treat that state as being an element of some set of states. And that's kind of the perspective that the standard, Hilbert space picture based on set theory gives you. And then you can also transform between different states of that system by applying operators, but somehow those operators are treated as secondary. What really matters is the space of states. Whereas in category theory, one has exactly the opposite perspective, that it's the processes, the operations that evolve the system in time that are really fundamental. And the current state of the system is secondary, right? So in the categorical picture of quantum mechanics, it's the arrows, the transformations from one state of a quantum system to another that are actually the thing one cares about, the categorical formulation of quantum mechanics is all about how those different arrows compose, what their compositional properties are, what their algebraic structure is. And then the actual object, the state that the system is in at any given point in time, those are somehow secondary. Those are emergent from this kind of deeper language of processes. So it gives you a kind of dual perspective on what's really going on in physics. So in a sense, as I say, set theory is like a kind of static model where what matters is the state of a system, and category theory is kind of a more dynamic model where what matters are the transformations that the system can undergo.
Cool. So it sounds like, all right, you got some stuff, and the big difference between set theory and category theory is in category theory, that stuff is identified by the thing it's doing.
Right, exactly. And so in a sense, you're exactly right. So generally in category theory, one doesn't care so much about the internal structure of an object. One cares about just what it does, right? What transformations can it undergo? What actions can it perform? No, that's a very good way to think about it.
Cool. And since I'm very ADD, we're going to jump back to a question we had in the chat that I also am curious about. And Fish Spider asked, what properties would rewriting rules need to have to match our universe?
Yeah, that's a really interesting question. So, I mean, obviously the answer is we don't know, in large part because we don't understand, at least I claim we don't understand the structure of our universe well enough to give a fully coherent answer to that right now. But we have, there are some things which we're pretty confident any convincing model of physics, properties that any reasonable model for quantum gravity ought to satisfy, right? So if one proposes a model for quantum gravity, it had better be the case that it reproduces, general relativity in the large scale limit, in the limit of large mass displacement. It had better be the case that it reproduces quantum mechanics and quantum field theory in the small scale limit, in the limit of small mass displacement, things like that. And there are other kind of more subtle technical conditions, like the fact that it should reproduce things like the holographic principle, right? The holographic principle is, at this point, pretty well established as being a sort of a no-go condition that any plausible model for quantum gravity ought to satisfy. So we have maybe a list of 5 or 6 criteria that we're pretty sure, that any sort of any reasonable model for our universe should obey. There's absolutely no reason to believe that those criteria are complete or even close to being complete, but we have some reason to believe they are at least correct. And so I kind of already mentioned, so then the question that Fish Spider asks is effectively then, what properties of these abstract rewriting rules will map to those characteristics that we think our universe obeys? And so then that, I kind of already alluded to a few instances of where we know the answer to that. So for instance, I already mentioned that in order to reproduce special relativity, we need to have this property of sort of causal invariance, that we have to have the property that the order of application of the rewrite rules doesn't affect the structure of the causal graph. I also mentioned that to derive general relativity in the large scale limit, you also have to have these additional properties that the causal graph limits to something that's finite dimensional, and that it has this weak ergodicity property in the underlying network dynamics. To get quantum mechanics, there's a different set of criteria that have to be obeyed. So there, it's all about getting the right compositional structure of the multiway systems. So this is a slightly more technical mathematical condition, but it all has to do with the essential difference that classical physics has with quantum mechanics. So the categorical picture of quantum mechanics gives you a pretty good intuition for what the essential difference is between classical physics and quantum physics, which is all to do with how different systems or different subsystems compose. So mathematically, when you've got 2 different subsystems and you want to, so say you've got, I have particle A and particle B, and I want to consider the composite system that's given by both particle A and particle B together, potentially interacting. There's a sort of standard way that you would get if you know the space of states for particle A and you know the space of states for particle B, there's a standard way that you get the space of states for particles A and B, which is that you do this operation called a tensor product. You take the tensor product of the 2 spaces of states and you get the space of states of the composite system. And if particles A and B are treated purely classically, then that tensor product operation has this very simple structure. It becomes what's called a Cartesian product. And the important feature that Cartesian products have is that it's possible to separate out the subsystems again. So if you take the Cartesian product of this space of states for A and the space of states for B, then you can do what's called a partial trace operation and recover the space of states for A or the space of states for B after you've taken the product. On the other hand, if particles A and B are treated quantum mechanically, you no longer have a pure Cartesian product. You have what's called a Kronecker product. And the special feature of a Kronecker product is that you can't do that. Once you've taken the Kronecker product, you can't neatly separate out the two subspaces again. If you tried to take a partial trace, you would only recover some of the information. And this is the essence of basic. Sorry, please.
No. You were just about to say what I was about to ask, I believe. Is this the measurement limit or the measurement problem?
So it relates to the measurement problem in a slightly subtle way, but yes, I mean, in a sense, everything that you think of as being, people like to go on about how quantum mechanics is fundamentally weird and counterintuitive and so on. And basically all the apparently weird and counterintuitive things about quantum mechanics follow from this basic fact to do with the algebra of states. It comes from the fact that, unlike with classical physics, when you compose different subsystems together, the product that you're taking is not a simple Cartesian product. It's this much more messy Kronecker product kind of operation. So this is the essence, for instance, of things like quantum entanglement. It's the reason why you can have quantum mechanical systems that consist of two particles, but where to describe the system, you can't neatly sort of separate one particle from the other. They're somehow inextricably linked. You need both in order to describe the composite system. That's a direct manifestation of the statement that this product is not Cartesian. So yeah, in a slightly subtle way, it is related to the measurement problem, because it's okay. What you're describing as the measurement problem is the statement that when you perform measurements in quantum mechanics, you can have the situation where the order in which you apply the measurement operations matters. You have what's called non-commutation of the observables. So ordinarily, if I have a classical, if I have a system that's described by classical physics and I measure variable X and then I measure variable Y, I get the same answer as if I measured variable Y and then measured variable X. It doesn't matter what the order was. In quantum mechanics, that doesn't happen. You can have what's called non-commutation of those observations. And kind of as you alluded to, the reason at some abstract level, the reason why that non-commutation of observables occurs is also a kind of an indirect consequence of the fact that you're composing your subsystems in a slightly complicated way.
Is that because we're using matrices?
So no, crucially not, right? And that's one of the core observations behind the category theoretic picture of quantum mechanics. So you're exactly right. The way that quantum mechanics usually gets taught is that every sort of state of your quantum system is some vector, right? Or some collection of vectors, what's called an array in some Hilbert space. And then the processes that you perform, the operations you perform, are then described by matrices, or more generally by bounded linear operators in the finite dimension, in the infinite dimensional case. So you might think, okay, well, therefore matrices and vectors and things must be somehow fundamental to quantum mechanics. Turns out that's not really true. And this is precisely the idea behind categorical quantum mechanics. So the idea there is that there are some features of vectors and matrices and things that are nice and that correctly capture features of real quantum mechanical systems. So one of those is that we can compose them, right? So if we have two matrices, and one matrix is evolving particle A and one matrix is evolving particle B. If I want to write a big matrix that describes the evolution of both particles A and B, I can take the tensor product of those matrices and I get this composite that describes the evolution of the combined system. And similarly, there are other operations I can do. Like if I want to reverse the direction of time, I can take what's called an adjoint or a conjugate transpose of my matrix, and that gives me another matrix that does the same operation but with the time direction reversed. There are these various algebraic operations you can do on matrices that reflect real operations that you can do with quantum mechanical systems, like time reversal or like composition. But one of the insights with categorical quantum mechanics is that you don't need matrices in order to do that. That any category that lets you compose objects in sequence, compose objects in parallel, and that has these additional algebraic operations like the time reversal operation, any such category will let you do quantum mechanics. And so the category of matrices and vector spaces is only one example of such a category. And there are many others. There are many more general settings in which you could do this. So, for instance, in quantum information theory, it's quite common that one describes quantum processes not in terms of matrices at all, but just rather in terms of these more abstract tensor networks. And the reason we know that that works is because there's a functorial transformation between the category of these tensor networks and the category of these kind of these Hilbert spaces with their traditional vectors and matrices and things. And anyway, so sorry, to come back to the previous question, the reason I mention all of this is that we now know sort of the conditions under which a set of rewriting rules gives you a multi-way system with the appropriate algebraic properties that lets you compose processes in sequence and in parallel in the way that you need in order to be able to do categorical quantum mechanics. So we have a pretty good picture of kind of I would say we have a pretty good picture of some sufficient conditions. Sorry, we have a pretty good picture of some necessary conditions for what it would mean, for what one would need from a discrete model for it to match our universe, but we certainly don't have a sufficient set of conditions, and I'm not even sure it's particularly close.
So when you say utilizing the tensor products and everything, as far as I understand it, basically a tensor is basically something that you can, whatever thing you are dealing with, it can go through, whether it's higher dimensionality, lower dimensionality. It's some summation that of the force and or what's going on with that thing between different perspectives.
So the way I would characterize the sort of the tensor product operation abstractly is just in terms of parallel composition, right? So if we've got if you think of a set of processes, so you've got okay, let's think of the simplest example, right? You've got like a system, it can be in state A, and then it transforms into state B, and there's another operation that takes the system in state B and transforms it into state C. Then you can clearly compose those two processes sequentially to get you directly from A to C. That gives you something that's akin to just ordinary matrix multiplication. That's matrix multiplication is like the kind of sequential composition of processes.
So steps of making a peanut butter and jelly sandwich.
Right, exactly. So you spread the peanut butter first, then you spread the jelly, and so the composition of those two.
We won't cause too much controversy by listing them all, but yeah, I got you. Right,
gets you directly to the peanut and butter and jelly sandwich. But then there's another notion of composition that's also crucially important, which is that. So suppose you had two systems now. Suppose you're making two different sandwiches, and so that there's one process that maps a system in state A to a system in state B, and another process that maps a system in state C to a system in state D. Then the question is, what happens if I try to do them both in parallel? Then I've got a single process that maps the composite of states A and C to the composite of states B and D. And the way I get that is through this generalized tensor product operation. So really, I mean, you can think of tensor products in all kinds of complicated, fancy mathematical ways, but the essential insight of category theory, or specifically of monoidal category theory, is that the essence of what it means to be a tensor product is that it's all about how you compose operations in parallel rather than composing them in sequence. And as I say, the essence of quantum mechanics is that when you compose operations in parallel that are quantum mechanical, the composite operation you get doesn't let you separate the two sub-operations that you started. It doesn't let you. There isn't a straightforward procedure by which you can separate the composite operation into the sub-operations that you composed it from. Once you've taken the composition, you're essentially kind of locked in. You can't neatly separate it out again. And that crucial observation that the parallel composition gives you a non-separable state is really the essence of what it means to be quantum mechanical. As a system.
So it's basically you're non-classical. You just go. Basically, these things are happening in some form of a series. I believe you used the word parallel. Series probably means something actually different depending on what we're talking about. But basically, whatever the product you get, you basically can't undo it.
Right, exactly. Which is the point of departure from our standard classical intuitions about physics. So, if you think about a classical, suppose you have, two particles treated classically. If I put them together into a box, I can describe both particles by using some composite mathematical description. I can describe the space of states of both particles together. But because it's a classical system, I can always neatly separate it into, this is the space of states of this particle, and this is the space of states of the other particle. But if those two particles are quantum mechanical, then they can become entangled. And then we can have the situation where the state of one particle actually is correlated to the state of the other particle. And so once you've composed them together, you can't separate them out again because the state of one depends in some very non-trivial way on the state of the other one. And as I say, mathematically, all of that means is that when we compose the two processes in parallel, they have this non-separable tensor product operation, the Kronecker product, rather than the standard separable tensor product operation, which is the Cartesian product. And so the nice feature about these discrete models is that we have a direct sort of picture of what that means in the context of multiway systems. There are rules for how you can compose different multiway systems and different multiway processes. And we have a very precise kind of graph theoretic characterization of what it means to be a Cartesian product versus what it means to be a Kronecker product. And we can even quantify sort of how quantum mechanical a given discrete system is based on how much the composition operation deviates from being a Cartesian product. And I mean, the basic idea is that if your multiway systems are purely tree-like, and you compose them just by kind of gluing them at the root of the trees, then that's the model of the kind of the most basic classical Cartesian product. As soon as they have non-trivial merging, as soon as they're no longer tree-like, as soon as they glue together when you compose them, then you get something that's more and more, that's increasingly like a Kronecker product. That gluing together of different multiway branches is essentially, therefore, the essence of quantum mechanics in this particular model.
So basically, once you have that additional complexity, you can go from something, you go from your A to your B, and then as soon as you have some evolution for whatever particular rule it is, goes on long enough, you start having it come back together. I find that very interesting. And the sheer fact that you can literally, as we've seen with Rule 30, get what appears to be like, I don't know, P equals NP. It's just, you need to actually go through the process, as far as we know now, to basically just continue on in order to actually figure out what's happening.
Right. Yeah, no, exactly. And so but this is, this is a different kind of complexity to the form of complexity that one sees in a deterministic system like Rule 30. So what you're referring to, Memes, in your sort of reference to Rule 30 is what we might call sort of computational irreducibility in a kind of classical setting, right? Where because we don't actually know that Rule 30 is capable of universal computation, but there's a pretty good I think there's pretty good evidence that it is in fact Turing complete. And so in a sense, okay, so I'm trying to work out what level should I pitch this explanation at. So in some sense, the reason, one more philosophical perspective on why the behavior of Rule 30 looks complicated is because if it is capable of universal computation, and if human brains are just universal Turing machines, then in a sense, what that's telling you is that the computation that our brains are performing is no more sophisticated than the computation that Rule 30 is performing. And in a sense, one can think of the process of doing science, or the process of perceiving and analyzing the world, as being kind of a computational battle between our processes of perception and analysis as observers and the processes by which the systems we're observing are undergoing in their evolution. And so ordinarily, science traditionally has tended to make the assumption that we as observers are kind of infinitely computationally sophisticated relative to the systems that we're observing. And for simple systems, that's a pretty good approximation, because we're, as far as we can tell, we're universal computers, and the systems we're observing are usually quite simple ones, like two-body gravitational systems or helium atoms or whatever. And so then we can so it's pretty reasonable to assume that we are able to shortcut the process of computation that the system we're observing is doing, and therefore its behavior looks to us simple because we can easily decode what's happening. But as soon as that isn't the case, like in the case of Rule 30, it will inevitably look complicated because we can't do that shortcutting anymore. That's, in a sense, the essence of computational irreducibility. But what we're talking about here in the context of quantum mechanics is another level of complexity. It's a complexity not just in the behavior of the system, but in how the possible evolution histories for that system branch and merge. And so it's in a sense, one is referring to kind of classical deterministic computation, and this is now a model of complexity that's based on something that's much more like quantum computation. But maybe we can talk about that in more detail.
Right. Well, my basic, and again, once you started to go into that, I brought up one of the papers there, um, and I just again, as you're seeing things evolve over time, it's like, all right, you got these things kind of merging, and I'm like, okay, that's very interesting. I'm looking at this thing. I'm looking at this at what on a flat screen, which appears to be 2 dimensions to me, and in order to actually, we got to get to Kutov's question. He truly believes we live in a non-fractal 2D universe. So let me pitch this to you, Jonathan. Keeping Kotov's question in mind about a 2D universe, how do we get from this to something like this? Does that question
Okay.
even make any sense?
Well, I mean, it depends on what Kotov precisely means by a non-fractal 2D universe. I mean, there's pretty good reason to believe that at least on a macroscopic scale, our universe does have 3 spatial dimensions rather than 2. So, for instance, one of the reasons why we're pretty sure we know that is that I mean, it's an experiment you can do in your own house. If you take a load of gas and a collection of gas molecules and you just let them diffuse, they diffuse out in a kind of ball or sphere,
Right.
and then you can just look at how does the volume of that ball or sphere vary with its radius. And when you do this on a macroscopic scale, you discover that the volume scales like 4/3 times pi times the radius cubed. And so the fact that it's the radius cubed is telling you that the gas is diffusing in at least 3 spatial dimensions. So there's pretty good reason to believe that we don't live in a 2 spatial dimensional universe, or even a 1 + 1 spatial dimensional universe, which would be even worse.
So let me take that question and reformulate it a little bit.
Mhm.
How can we take perhaps a representation, or is it possible to do some representation of what we experience in our 3+1 dimensional universe as far as most folks and we understand it currently? Is there a way to model that and then transfer? Because I've heard some of the lectures from Professor Witten, and he just some of these things he hammers. Do I understand all the math? No, not at all. But I find it very fascinating that seems to be a thing.
Right. Okay. So right. Okay. So maybe it's worth mentioning something about the holographic principle, given that this is, I think, the source of a lot of these ideas about sort of encoding, higher dimensional physics on kind of lower dimensional surfaces, which I think is kind of what you're referring to here. So the origins of this idea really go back to questions related to the black hole information paradox. So there's this fundamental problem in black hole physics, which is that black holes are they're valid solutions to the Einstein field equations. We're now pretty sure that they exist in our universe, but they appear to be incompatible. One of the features of black holes is that they hint at a fundamental incompatibility between general relativity and quantum mechanics. Specifically, they hinted an incompatibility between the notion of event horizons in a black hole and the notion of unitarity or unitary evolution in quantum mechanics. So unitarity is this fundamental principle of quantum mechanics. And one of its implications is that you can't destroy information, right? That once information, if you have quantum information in our universe, if you have a collection of qubits or something, you can't destroy the information that those qubits encode. If you could, it would violate unitarity. It would violate one of the core axioms that we think our universe obeys. So imagine you've got a black hole and you chuck something in. You chuck in a book or some object that definitely encodes a certain amount of information. Mm-hmm. It then that book passes the event horizon, gets crushed into the singularity. It contributes to the mass of the black hole. Now we have pretty good reason to believe that because of quantum effects that occur near the horizon, that black hole will gradually radiate out some of its mass through this process of Hawking radiation. The problem is that radiation will occur at the event horizon, or actually, in fact, just beyond the event horizon, that's to say, just on the outside. And so once the information inside the book has passed the event horizon, that information can't get out again, right? Because to do so violates special relativity. So we can deduce that whatever particles of Hawking radiation get radiated from the horizon, they can't encode any of the information that was encoded in the book, because if they could, then that information would have had to cross the event horizon, and that would violate special relativity. But then we have this paradox now, where now the black hole is going to evaporate away to zero. So where did the information go? you've got a bunch of particles that came out that can't, as far as we can tell, be correlated with the particles that went in, and yet the book has disappeared. You've destroyed information. You appear to have violated unitarity, right? So this is the black hole information paradox. And it was quickly realized, so there was a famous calculation done by Stephen Hawking and Jacob Bekenstein called the Bekenstein-Hawking entropy formula, or Bekenstein-Hawking relation, that implied that information could be encoded inside event, sort of at the surface of the event horizon. Because in a sense, okay, what's going on is when you throw the book into the black hole, you're contributing to its mass. So, and the more massive a black hole is, the larger its event horizon will be, because the larger its Schwarzschild radius is. And so for every sort of bit of quantum information that you add to a black hole, for every bit of entropy you add to a black hole, the event horizon grows by a certain amount. But the really bizarre thing is that the Bekenstein-Hawking formula tells you it doesn't grow. It's not that the volume of the event horizon grows. It's actually that the area of the event horizon grows. It grows by an amount that's proportional to a Planck length squared, which is an area quantity. So what that's telling you is that if you want to resolve the black hole information paradox, one of the most natural ways to do it is to say that somehow the information about what you threw into the black hole is being encoded not on the interior, but actually on the surface. And if you postulate this, and so because of the Bekenstein-Hawking formula, it's kind of mathematically consistent to say that, as long as you postulate that, then there's no problem anymore. Now it's perfectly possible for the Hawking radiation to be correlated, the outgoing particles of Hawking radiation to be correlated with the bits of information that went into the black hole in the first place, and you've resolved the problem. But you're now led to this very, very bizarre ontology where somehow this two-dimensional surface, the boundary of the black hole, is encoding information about what's on the interior, which is three-dimensional. And so, the analogy that's often used is it's like saying that you could know, you could have all the information about all the books in the Library of Alexandria just by knowing about the structure of the walls and the ceiling and the floor. It's really a very counterintuitive idea that somehow three-dimensional information could be encoded on a two-dimensional surface. But this is the essence of the holographic principle. And so its most concrete sort of mathematical formulation is in terms of what's called the ADS-CFT correspondence, the idea that ADS, which is that is to say anti-de Sitter space, which is a kind of a geometrical gravity theory that can exist on the interior of a surface, that can be encoded in terms of what's called a CFT, a conformal field theory defined on the boundary of that surface. So you can have in the 1 + 1 dimensional case, which is the case where ADS-CFT has kind of been studied most rigorously, you could imagine something that looks a bit like a soup can. So you've got like a sort of you've got a cylinder, so you've got a bulk gravity theory on the interior of the soup can, and you've got a sort of quantum field theory on the boundary of the soup can. And somehow, just by knowing the quantum field theory on the boundary, you can determine everything about the gravity theory on the interior. And so it's in cases like this where, as you correctly allude to, the notion of whether the universe is really three-dimensional or really two-dimensional becomes a little bit subtle, because you could say, well, the sort of gravitational part of the universe, the bulk part, is three-dimensional, but the quantum field theoretic bit that encodes that bulk theory could itself be two-dimensional. Everything going on in the three-dimensional universe could be encoded on a two-dimensional surface at the cosmic horizon.
If we have a proper label on the can, will we be able to tell the soup on the inside?
Yes, right, exactly. That's precisely the point, right? That everything there is to know about the soup, you can infer just by knowing the label on the exterior. Yeah, that's the idea.
We just don't want to have the wrong label, because then we're going to be eating something that we didn't plan on. But right. See, that was fascinating, and that was actually part of the bit, because this was around the time where I think there was some new data from maybe like the beauty quark or something like that. People talking about a fifth force or something going on, and I remember during the project at one point I think you were talking something very similar to this, because I included in the video something about where the volume increased and something about the surface area to the volume, and as you were saying, like, it really wasn't intuitive. Could you kind of like explain that a little bit more so I can kind of grasp my head around that?
Sure. So I think the particular thing that was being discussed in that in the video clip that you mentioned. So, one of the features of these discrete underlying models of space and of space-time is that these notions of dimension become much more fuzzy, because in a sense, if you just have a network, if you just have information about points and how they're related to each other, then there's no a priori notion of dimension. You can lay out a network in on a flat two-dimensional surface. You can lay it out in 3 dimensions. You can lay it out in 4 dimensions. But there's nothing in the structure of the network itself that tells you how it should be laid out. It's all just kind of essentially it's just a visualization trick. There is a way that you can deduce sort of internally what the network, what the dimensionality of the network is, but it's a slightly approximate and coarse-grained method. And sort of the standard way to do it is you exploit the fact that in ordinary spaces there's this nice relationship between volumes and dimensions. So if you so suppose you've got a network and you want to know how many dimensions it's in, or how many dimensions it encodes. One of the ways you could do that is you just pick a point and you look at the points adjacent to it and the points adjacent to those, and you grow out some kind of circle or sphere or ball or whatever. And if the network is kind of flat and two-dimensional, then the volume will grow like the area of a sphere, like the area of a circle, like pi r squared. If it's sort of a 3-dimensional network, it will grow like the volume of a sphere, 4/3 pi r cubed. And in general, in d dimensions, it'll grow like r to the d. And so if you flip that around, if you take logarithmic difference estimators, you can infer what the dimension d is just by looking at the growth rate of a volume of a ball. But there are some subtleties there, and because this notion of dimension is what in mathematics we call Hausdorff dimension, and it's only one notion of it's the notion of dimension you get by looking at sort of exponents of volumes, and it permits some interesting things. For one thing, it permits non-integer numbers of dimensions, so you can have fractional dimensions, which are the basis of kind of fractal geometry. But also for the case of these discrete networks, or these models of space-time based on discrete mathematics, they allow you to have dimensions that are actually different in different regions of space. So traditionally, we think of space as being kind of homogeneously 3-dimensional for no other reason than in continuous mathematics, dimension is assumed to be continuous everywhere. In the sort of ordinary theory of manifolds, dimension is what's called a local invariant, which means you can't have sort of different regions of the same connected component having different dimensions. But in a network model, in a discrete model, that's no longer a constraint. You can have one pocket of the universe that's 3.01 dimensional and another pocket that's 2.99 dimensional, and there's no problem at all with that. And so what we were discussing in the particular video that you allude to is this question of essentially, what would cosmology look like in a universe where this notion of dimension is a bit less, is a bit more weak, is slightly more subtle. And so, for instance, one thing is that the higher the dimensionality of space, the more causally connected the space is. So, if you take some network and you add more and more long range connections between a single point and the points around it, you're effectively increasing the local dimension in that particular region. And so one of the consequences of that is that if you consider what does cosmology look like in a universe, say, that starts very high dimensional and gradually converges down, it starts to look something that you get a universe that looks a lot like a kind of that looks like it's obeying an inflationary model of cosmology. And in fact, there's a way that you can make that precise. That is, the conformal structure you get of a universe that starts in high dimensions and converges down is equivalent in a certain class of cases to a model of cosmology called VSL that's due to Pettit and Olbrecht, a variable speed of light cosmology, where effectively the universe starts off very causally connected and becomes progressively less causally connected. And it's already known that those models of cosmology reproduce the conformal structure that we see in sort of inflationary models. So in other words, they are sufficient to solve the horizon and flatness problems that one gets in lambda CDM. And so I think in that particular video, what we were trying to get to the bottom of is essentially, how would one go about constructing a sort of mathematically rigorous model of cosmology in these cases where dimension is no longer a local invariant?
What are your thoughts about electromagnetism being possibly misunderstood as dark matter? It comes from McCracken.
I don't have any particular thoughts on that. I mean, so it's a little bit hard to see how that could work. So, there are various reasons for why one believes dark matter exists, but one of them is these observations of galactic rotation curves, right? So if you look at how stars orbit the sort of centers of galaxies, they appear to be orbiting much faster than you would expect them to orbit, given the sort of visible luminous matter we can see inside those galaxies. And so if you just run a computer model with the mass of the galaxy being concentrated only in the luminous matter, in the matter that we can see, then based on the velocities and based on the rotation curves that we actually observe, using sort of redshift data, those galaxies should rip themselves apart almost immediately. So there's, in effect, what's happening is that the rotation curves are, as you can see in those pictures, much flatter than we'd expect them to be just based on the luminous matter that one sees. And so one of the resolutions to that problem is to say, well, maybe there's some matter that we can't see that's extending the galactic halo enough to flatten out these rotation curves. And you can sort of mathematically model how that would work. And based on extrapolating how much you'd need to extend the gravitational halo, you can work out what the ratio of the invisible matter contribution is to the luminous matter. And this gives you a calculation for rough, sort of a crude way of computing what the ratio of dark matter to baryonic matter would be in the universe.
So that's kind of where we get, sorry to cut you off, that's kind of where we get all right, there's got to be like 4 times more dark matter approximately within that, but than what we visibly see.
Exactly. Okay. So those inventories where you can see, this is the proportion of dark energy, this is the proportion of dark matter, this is the proportion of luminous or baryonic matter. Exactly. That's how those ratios are computed. And so, but the important point there is that in order for dark matter to be able to flatten these galactic rotation curves, whatever it is has to be able to interact gravitationally. So having it be some weird manifestation of electromagnetism. I mean, I'm not an astrophysicist, so I'm not going to say that it can't work. But
let me reformulate this. And this is based upon some of the things I've heard before, because I keep hearing that a lot of the times when you're looking at some of the equations for electromagnetism, it kind of sort of lines up with gravity to a point. And then I think you said we run to like the ultraviolet thing, or like, what's that thing? It seems to be very simple because it's because once you get to distance, so much distance away, it's like, okay, now you're kind of taking the square root of that. It's losing force. But it doesn't, it's not electromagnetism. It's something different, but it follows a similar look, if you would.
Right. So certainly classically, gravitation and electromagnetism look extremely similar. I mean, Newton's law of gravitation and Coulomb's law of electromagnetic sort of attraction and repulsion are exactly the same equation, just with mass replaced by charge. But sort of there are some fundamental differences that only become more profound as you investigate the kind of quantum field theoretic basis of them. So one of the really important differences is that in sort of the standard way we think about gravity in the context of general relativity, there's no such thing as a negative gravitational charge, right? There are only positive gravitational charges, masses. Whereas in electromagnetism, you can have both negative and positive electromagnetic charges. And that's actually really important for things like how one detects photons. This is the basis of quite a famous paper by Freeman Dyson, in which he argued that you couldn't sort of effectively detect gravitons if they existed using the same method that one uses to detect photons, because the sort of standard techniques that one uses for detecting photons that were due to Bohr, and I think the paper was originally by Bohr and Rosenfeld, where they introduced this idea of what's called compensation, where in your kind of photon detector, you need to have a way of compensating for the induced electromagnetic fields by the detection apparatus. And the way that you do that is by balancing the charge, by using an equal and opposite charge on the other side. And the whole point is that because you can't have negative masses in general relativity, you can't do, the notion of this compensation doesn't exist in gravitational theories. And that's really important because it puts hard limits on how effectively one can observe gravitons. And in particular, it means that it's effectively impossible to set up the Bohr-Rosenfeld apparatus for detecting gravitational interactions.
I mean, would there be, in theory, any potential way to kind of get around that at all, or? Or is it just not work? Is this one of those things where it's like you will go into an infinite loop, or you run into like an issue, or you just can't do it just because you can't go the other way?
I mean, I don't think we understand, or at least suddenly I don't understand either electromagnetism or gravity well enough to be able to definitively say. All I can say is that yes, so classically they obey essentially the same system of equations. But at a kind of more foundational level, there are key differences that mean I'm a little bit skeptical about. So something like dark matter, which is such a fundamentally gravitational hypothesis, I'm a little bit skeptical about whether that problem could be effectively solved using something related purely to electromagnetism that didn't involve gravity at all.
Yeah, I was gonna say. I mean, well, I mean, dark matter does exist. I mean, there are neutrinos and stuff, but then again, how many neutrinos would it take to account for 4 times of what we're basically actually viewing? That's a lot of neutrinos. So it's
Yeah,
I don't know.
yeah, definitely.
But Jonathan, we've been going for a little more over an hour and stuff. I know your time is valuable. I know it's getting pretty late over there. Any other topics you wanted to touch upon? Any questions in the chat that really jump out to you as far as your interest
I don't think
goes?
so. I've been trying to ignore the chat because I find it slightly too distracting. But if you think there are any comments or questions that came up,
The reason why I asked is because I'm terrible with my own chat and everything as well. A lot of times I'll just come on, just kind of do a quick spiel, kind of like hop on Wolfram Alpha, just kind of look at a couple of different things, because otherwise I'm the exact same way. I get completely thrown off. That's one of the reasons I like to have other people up here so they can talk and I can do something else so my mind doesn't get distracted. It's I like to pitch as, oh, I'm collapsing my own wave function. I'm throwing myself off. Okay, how about this? Let's maybe wrap up with something a little bit more satiable for maybe a broader audience, maybe a little bit of philosophy. Let me actually read one of the questions that I actually wrote down somewhere.
let's go for it.
Okay. One, what is your favorite color?
My favorite color. That's an interesting question. For some reason, I always find blue very relaxing. So I'll go with kind of light blue.
Blue is the best flavor. How about this? Okay, we started off with who are you? I'm going to finish up on the darker side of the great maker J. Michael Straczynski. What do you want?
What do I want? That's an interesting question. I don't see why that's necessarily darker. I mean,
it comes from the shadows in the series. I'm sorry. Continue.
Oh gosh, this is a reference I'm unfamiliar with. I apologize. I guess, I mean, so all I can say is that the primary thing which I'd say motivates me is that I just really like I like to understand things, right? I like to try to, if there's a thing that I don't understand, I feel extremely kind of motivated to try to get to the bottom of it. And so as a consequence, I guess I've sort of tried to optimize my life in such a way that I can spend as much of my time as possible doing things that I find intellectually sort of stimulating. And in a sense, you know, the major thing that I want is to try to do more of that, right? I have a large backlog of projects of things I want to try to figure out, things I want to understand, things I want to write up, things I want to learn about. And you know, the main thing that's kind of driving me at the moment is trying to figure out how do I do more and more of those projects on that list, and how do I optimize things so that I can do, you know, I can figure things out more effectively and more quickly. And I'd say, you know, to a large extent, more so than any other factor, that, you know, it's really it's those things that kind of that get me out of bed in the morning and that make me excited to do what I do.
Jonathan Gorard, thank you so very much. And again, during the stream, we have not proven
it's turtles all the way down.
Not yet. But that's all I got. Thank you so much. I'm going to add the links to Jonathan's papers after this. I totally messed up and didn't do it before. Feel free to browse some of the stuff. I read one of the more recent papers on GR, as well as I saw that thing on quantum circuits, and it's completely fascinating. So by all means, check it out. Other than that, peace out, everybody. Be safe. We'll catch you all next time on Science Week.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.